Chemistry is a discipline that is heavily focused on solving problems, not just in school, but also in research, product development, and manufacturing too. Most of the time, students are left to their own devices to figure out effective strategies for solving problems by trial and error and through lots of practice, until the process becomes intuitive. Fortunately, a Hungarian mathematician named George Polya wrote a book summarizing the technique that many people adopted without even realizing it. This lecture is a brief summary of the major points in Polya's book. The 7 steps to solving a problem starts with restating the goal. It's surprisingly easy to get caught up in the solving process and lose track of what we're trying to find in the end. So make sure you know what the answer looks like and what the units are expected. Step 2 is making an estimate of what the answer should be. Sometimes this can be a really rough guess, but other times you might be able to make a reasonable estimate. The purpose is to alert you if your calculated answer at the end is very far off from your estimate. In the beginning, this will be difficult for you, but with practice, you'll get much better at it. Next, we review the data. Write down the information that comes with the problem, and think about any other standard data that you may be able to look up to help you. Step 4 is counterintuitive, but it's really important to start from the answer and work the problem backwards, at least conceptually. Ask yourself, what kind of information would I need to know to calculate this answer? That will help you to define an intermediate value to calculate on the way to the final answer. Keep doing this until you can find the pathway back to values that are either known from the problem or things that are easily looked up. Remember, you have much more data in your smartphone today than the best engineers had when we sent astronauts to the moon and back. Step 6 is turning the problem around and following that same path back to the answer, this time computationally. The final step is checking your answer. Does this answer agree with your estimate? Is it a reasonable value? Does it pass the smell test? If so, it's probably correct. If you were going to make an error, it's likely that you would make a big one, and you should catch it at this point. Let's take a simple example. In fact, this example is so familiar that you probably don't even recognize that you're using this technique in solving this kind of problem. You and 4 friends are studying together, and you order out for pizza. Each of the 2 pizzas costs $12.95 plus tax and tip. How much does each person owe if you split the total cost equally? Well, following the steps, you first make a rough estimate. Each pizza is about $13, so $26 for the food, and then round up generously to $30 for tax and tip. Split 5 ways should be about $6. You did this calculation before you agreed to the order, because if the estimate were $4,000, you might have gone home hungry instead. So now you work the problem backwards. To find your exact share, you would have to know the total cost. And to get that, you would have to know the cost of the food and add tax and tip as appropriate. And to know the cost of the food, you'd have to total up the cost of the 2 pizzas. So with this plan in mind, we now do the calculation forward, calculating the exact cost of the pizzas, then multiplying by 1.065 to get the cost plus tax, and then multiplying again by 1.2 for a 20% tip, and then finally dividing by 5 to get the cost per person of $6.62. The last step is to compare this with our estimate, which was a little bit low, but not too far off the mark, so we can have confidence that we did the calculation correctly. The second example is a chemistry problem where we have less intuition, but we'll follow the same procedure. We're told that a particular bronze alloy is composed of 86% copper by mass, and we're asked to calculate the mole fraction of tin, which comprises the balance of the alloy. Mole fraction is a unitless number, and we know that its value always lies between 0 and 1. The tin comprises only 14% by mass, and each tin atom weighs more than a copper atom. So we might estimate that the mole fraction is about half the fractional weight by mass, or about 0.07. Conversion between mass and moles always involves the molar mass, which has the same value as the atomic weight in AMU. So we look up these values for copper and tin and add them to our available information. Working backwards now, we know that we could calculate the mole fraction if we knew the number of moles of each component, and we could get those values from the number of grams using the molar masses, and those could be known if we knew the total mass and the mass fraction of the components. And so now we have the threat. Working forward, we encounter a minor obstacle that we don't know the total mass of the alloy. But the final answer, mole fraction, doesn't depend on the size, so we can make up any size we want. So we choose a convenient number like 100 grams. Next, we write down the masses of each metal and convert each of them to moles by dividing by the molar mass, and finally divide 0.118 moles of tin by the total number of moles to get a mole fraction of 0.0802. Is this a reasonable answer? Well, yes, it's quite close to our rough estimate, and definitely lies between 0 and 1. All we really need to do is round to two significant figures, because that's all we got for the mass fraction of each element in the data, and our final answer is 0.080 mole fraction of tin. I hope that you will follow this general method of solving problems. With lots of practice, you will become proficient at it, and it will help you to think intuitively about a difficult subject that many people struggle to understand. And that will make you very special indeed.